Hi everyone, welcome to our 13th lecture on the work due to friction and how it affects our conservation of energy law. This is a combined lecture. It's for both the Calc and the non-Calc students. Okay, so let me remind you a little bit of what we've done up till now. If you go back a couple of lectures, I introduced the work energy theorem, and the work energy theorem basically said that if you calculate the total work done on an object, then that's going to equal the change in its kinetic energy. And this law was universally applicable to all dynamical situations. Okay, but then we took the work and we actually split it into two pieces. We split it into a piece which was the work due to conservative forces, conservative because it conserves energy, work due to conservative forces, and the work due to non-conservative forces. And there was only one non-conservative force, and that was friction. Okay, and this lecture I'm going to tell you about the work due to non-conservative forces, but what we did in the previous lectures is we said let's pretend that there's no friction so that we have only the work due to conservative forces, and the work due to conservative forces we could actually write as a change in this quantity called the potential energy. And so the potential energy was a little bit like a bank account. You could store energy in potential energy, and then you could get it back again. And the simplest example of that is just raising an object off the ground. If there's an object here at this level, it has a certain potential energy due to gravity, and that's calculated by mgh. And then if I lift that at a higher level, then there's a energy due to gravity again, mgh, but because the height is bigger, there's more energy. And so it's like when I lifted it up, I put energy in. When I let go, I get the energy back. I lift it up, I put the energy in, I let go, and the energy comes back. And so this work due to the conservative forces could be written as a difference in the potential energy at two different points. The other potential energy we looked at was a spring. And so, you had a spring and say it was compressed a little bit, it has a certain amount of potential energy, but then I can compress it more and I put more energy into it, and then I let go, and that energy comes back, and so on. So this is why I use the analogy of a bank account, because you could put energy in and get energy back out. When you got the energy back out, then that would become energy like kinetic energy. Okay, so if you have a compressed spring and you let go, then that energy of the compressed spring could go into the kinetic energy of pushing a block forward. This is kind of like that pinball machine example that I did. All right. But now we have to turn to the work due to friction. The work due to friction basically breaks conservation of energy. Now, it's not really that energy disappears. Energy is conserved just like mass is conserved, okay? So from chemistry, if you do a chemical reaction and you have, say, 10 grams of reagent before, and some reaction occurs, there's still going to be 10 grams of reagent after. Mass doesn't appear or disappear. It turns out that the same thing is true with energy, but there is one place that energy can go that it's really hard to detect, and that's heat. Okay, and so sometimes people will say that the energy is lost to heat, which is probably not the best way to say it. I might even say it sometimes. It's really that the energy is converted to heat, and when energy is heat, you don't really see it, and it looks like it went away. So let's go through the energies that we've looked at. Kinetic energy, something has kinetic energy because it's moving, and the bigger it is, the faster it's moving, the more kinetic energy it has, because kinetic energy is calculated by 1/2 mv squared. Okay, and that there's potential energy in something, not because you can see it moving, but just because you could see the configuration. So when something is low near the ground, you know that it has less gravitational potential energy when it's up high. Or same thing with a spring. You can tell that there's energy in the spring because the more you compress it, the more energy there is, or the more you stretch it, the more energy there is. But heat is a little harder to see the energy. I mean, you can touch it and you'll know that it's hot. But early physicists before Joule didn't know about this. Charles Joule discovered that heat was a form of energy. Early physicists didn't know that, and they said, well, this friction is kind of messing things up. It's making the energy go away. Until they discovered that it was just becoming heat, they really couldn't say that energy is always conserved. Okay, so we're going to finish this story next semester, so I don't want to go too far down the path of heat, but I do want to tell you what's happening here. The friction is converting the energy into heat. And heat, unlike a potential energy, you can't treat it like a potential energy. It's not like a bank account. If you put energy into heat, it's not so easy to get it back. Again, a story for next semester when we study thermodynamics. But you'll see that actually as come out as I work out the work due to friction in this lecture. Okay, so let's just start with some equations here. So here we had the total work, okay? And I told you that that total work could be written as the work due to conservative forces here like that. And I just put conservative because a lot of forces are conservative. One that we haven't studied but will is the electrical force. It's also a conservative force. And then I just put the work due to friction here because it's the only non-conservative force that we're considering, okay? And we know how to calculate the work due to conservative forces. It's basically just that change in the potential energy. Actually, it's the negative of it because it's energy that you're taking out, okay? So that was easy. You know, again, back to my example of an object that's falling, mgh here, mgh here. So you just calculate mgh up here, mgh down there. The difference in those two mghs, different h's, there'll be different values. That difference, that was the work done due to gravity, okay? But how do you calculate the work due to friction? All right. And here's where things get complicated. All right. You can't calculate it as just an endpoint thing. If you could, actually, you'd be back to potential energy. You actually have to go back and calculate the work done by friction all along the path. Okay. It is not path independent. Conservation of energy, this is the whole point of a conservation law, is path independent. You have one state here, some initial state and some final state. And how you get from the initial to the final state does not matter. That was my roller coaster example where you could take many different paths down and it would still give you the same answer. But here with friction, it is path dependent, okay? Not totally path dependent, but there are some details that you have to bring in. Okay, so let's look at how to calculate the work due to friction. All right. So this is not a full story. A full story would not only require calculus, but it would require calculus beyond the type of calculus that most of you had studied. It actually require vector calculus, okay? So we're not going to do that. We're just going to do a simplified model of friction. And to do that, let's just consider, you know, a car here. Some mass m, and it's just moving along a road, okay? And all we're worried about is the fact that this mass was displaced the distance d, okay? All the while there was a force of friction, ff, force of kinetic friction, ff, in the opposite direction. That's that 180 degrees in there, okay? So the object is being displaced to the right. The force all the way along the displacement is to the left, and the angle in there is 180 degrees, okay? Go back to the original definition of work, which we really didn't use. I kind of introduced it, but I didn't really use it that much. I just kind of roughly did to show you why mgh is true. But now we're going to use it more directly. The work due to friction is going to equal the force of friction, because remember, work is force times the displacement multiplied by the cosine of the angle between d and f. Okay, so you've got the force of friction. There's your force. D is the distance of the displacement. The block is going to move from here to here. Okay, and cosine in the angle between the two is 180 degrees. Now, cosine of 180 degrees is one of those angles that you should have memorized. Cosine of 180 degrees is negative 1. Okay, and so all you get is a negative sign there like that. All right, now here we go. Since the force of friction is always 180 degrees to the displacement at every point in the path, you could just say, you know what, I'm just going to add up my minus ff times little delta d's all the way along here. Okay, and this diagram I'm trying to show you that, you know, the displacement is up, but the force of friction is 180 degrees back, displacement this way, 180 degrees back, and so on. So, you know, you just look at this entire path, and what you get is that the work due to the friction along the whole path is going to be the force of friction along the path multiplied by d, where d is the length of the entire path here like that. And I don't care how curvy it is, you got to measure that entire length. Okay, now you might say, how do I measure a curvy path? Well, in a problem I would give you the number. You'll see that in a minute. Experimentally, you could measure this by either, you know, maybe you could take a rope and just put the rope along the curvy path and then straighten out the rope, and you can measure it against the ruler. Or in track and field, they've got these wheels that turn, and every time it makes a turn, it's like 1 meter. And so you just, it's on a stick, so, you know, you just run it along the ground, and every time it turns 1 meter, 2 meter, 3 meters, 4 meters, and you just roll this thing all along the path, and again, you can measure a curvy path that way. So, you know, you've got that distance d, and you take that distance d and you multiply by the force of friction. The force of friction, you get the work due to friction. Okay. Now, this is a This is a gross simplification, but it's good enough for our purposes. Again, if you really wanted to do this correctly, you'd have to use this. You'd have to use a much more complicated technique of vector calculus, and we're just not going to go there. Okay, so now what? Well, now that we have this work due to friction, we can plug it above, and above we had that the change in the kinetic energy was equal to the total work. That was the work energy theorem. But then we break it up into work due to conservative forces and work due to friction. Okay, the work due to the conservative forces can be written as the change in the potential energy, negative the change in the potential energy. Okay, and now the work due to friction, our approximation of it. Okay, because again, this is like really not what would happen in the real world. You'd have to bring in a lot more details that we're not going to bring in. But that work due to friction, the way we'll calculate it is just minus FF times D. Okay, now what? Well, we can take that delta U and bring it to the other side the way we did before. And then on the left-hand side, you'd have your delta, including both K and U. In other words, both the kinetic energy and the potential energy. And the kinetic and the potential energy together is your total energy. So on the left-hand side, you have the change in the total energy, and that's going to equal the work due to friction. Okay? Uh, and here I've written it out a little bit more clearly. Your change in energy is going to be your final energy minus your initial energy. And that's going to equal minus the force of friction times the distance. Okay, so this is our modified form of our conservation due to energy. Energy is not conserved here. Okay, it's not conserved, and that's because it's disappearing as heat. Okay, the friction is making it disappear. Now, how do we see that? Well, if the friction were zero, then the right hand side here would be zero, and that can only be the case if your final energy is equal to your initial energy. That's what we did before. That's what we did up till now when we said energy was conserved. If the final energy is equal to the initial energy, then you have conservation of energy. But notice now that because the right-hand side is negative, a negative number, that means that your final energy has got to be less than your initial energy. So you start off with energy, say 100 joules, and then as the friction bleeds away that energy into heat, that 100 joules will become like 90, then 80, then 70, then 60, and so on, and the energy slowly disappears as heat. Okay, I say disappears in quotes because it's really becoming heat energy, but we don't know about that right now. Okay, so the final energy minus the initial energy is going to equal the work due to friction, and that work due to friction is negative. It means the friction takes away energy from the system. Okay, so this is the formula we're going to use. All right, again, this is the work energy theorem, but it's the work energy theorem where we've taken the conservative forces and lumped them in with the kinetic energy to talk about the total energy. And so it basically says the total energy, or sorry, the change in the total energy, that's just the work due to friction. Okay. All right, at this point we can do a problem, and these problems are fairly straightforward. You just have to recognize whether or not the energy is conserved, in which case at every point in the path you make sure that the energy is the same. Or if there's friction involved, well then the energy is not conserved. And I'm going to have to give you more information so that you can calculate whatever I want. Okay, so I just said, what, let's just reconsider the roller coaster example that we started with the very first time. Okay, and so in that roller coaster example, we had a roller coaster at the top of a roller coaster car at the top, and I said that it had a mass of 500 kilograms, and it started off with a velocity of 5 meters per second. Okay, at the very top. Okay, that was point A, and that point A was 100 meters above ground level, and then it goes down the track, and the track has some curviness to it, and then it gets to the bottom. Okay, and at the bottom, in this case, it has a velocity of 25 meters per second. I'm actually going to tell you how fast it's going at the bottom. And I call this point D just to make it correspond to the example that I did earlier. There I had a point A, a point B, and a point C, and a point D. But here we're just going to consider point A and point D. Okay, so that's the picture. Let's look at what I wrote with the English. A car of mass 500 kilograms starts at a point A with an initial velocity of 5 meters per second and goes downhill to point D, where it has a final velocity of 25 meters per second. The total distance traveled along the track is D is equal to 500 meters, while the vertical drop is 100 meters. Let's make sure we understand those two numbers. The vertical drop here is 100 meters. But if you were to measure the distance along this curvy path by the methods that I just mentioned, that total distance all along this curvy path here to there is 500 meters. Okay? So what do I want? I want you to find the force of friction, and I want you to find mu k. I should really say approximately mu k, okay? But that's all right. We'll just find mu k. All right, so first you say, well, how do I do that? In the conservation of energy, the energy was the same everywhere, but here it's not. In fact, we're going to make use of this formula right here because we're looking for friction. So it'd be good if we have d, right? If we had the initial velocity and the final velocity and we have d, we'd be able to find the force of friction. Okay, so let's do that. Let's start off by finding the final energy. The final energy, that's the energy at point D. Okay, E final, here's the energy at point D. It's all kinetic energy down there. Why? Well, if we take a look here, h equals 0, the height of 0, that's ground level. All right, there's ground level. And so if the roller coaster car is at ground level, then its h is 0 and it has no gravitational potential energy. There's no springs in this problem, so nothing about spring potential energy, but it's moving, and so all the energy must be kinetic, okay? And so the total energy at the bottom, the total final energy, it's just 1/2 mv squared, and plug in the numbers at that point. M is 500 kilograms, V is 25 meters per second, and that turns out to be an energy of 156,250 joules. Okay, a little over 156 kilojoules. All right, do the same thing at point A. Let's find the energy at point A. The energy at point A, that is your initial energy, right? That is your initial energy. And there you have both kinetic and gravitational potential energy. It's mostly gravitational potential energy, but there is a little bit of um, uh, velocity at the top at 5 meters per second. So there's a little bit of kinetic energy at the top. The kinetic energy is calculated using 1/2 mv squared. The gravitational potential energy is mgh. Okay, just substitute in the numbers. Mass is 500. Velocity was 5 at point A. 5 meters per second. Mass 500, G is 10. We're approximating 9.8 is 10. And H is 100 meters because it's 100 meters off ground level. And that turns out to be 506,250 joules. Okay, take a look at these two numbers. Energy is definitely not being conserved, right? Because the energy after is 506 kilojoules. And here it's 156 kilojoules, so that's quite a difference, right? That's like a 450 kilojoule difference there, all right? So where did that energy go? Well, the friction converted it into heat. All right, so we're going to use our formula that the final energy minus the initial energy is equal to the work due to friction minus FFD. Okay, our final energy from above was 156,250 joules. Our initial energy was 506,250 joules. I said 450 kilojoules. It's 350 kilojoules. Sorry about that. Okay, so 350 kilojoules. And the distance was 500. Okay, and so this reduces to a simple formula in which there's only a force of friction, and that gives us that the force of friction must be 700 newtons. Okay, an approximation, but gives us an idea that all the way along this track, in order to bleed off that energy such that you have only 25 meters per second at the bottom rather than what we found earlier, okay, you're going to have 700 newtons acting in the opposite direction to the displacement at every point along the track. Okay, and that gives us the force of friction. How would we get the coefficient of friction? Well, this was kind of a gratuitous addition to it. Unfortunately, the car is at different angles at different times, so I just said, let me just calculate the coefficient of friction when the car is on a level track, which occurs either at the beginning or at the end. Okay, so over here I just did a quick free body diagram. The weight of the car is mg is 500 times 10, which is 5,000 newtons, which means the normal force must be 5,000 newtons to cancel its weight. Okay, and the frictional force was 700 newtons, which we just calculated, and the coefficient of friction is basically the coefficient of kinetic friction, the little k there, is the force of friction divided by the normal force. 700 divided by 5,000 is 0.14. Okay, so like I said, just a little bit of a gratuitous addition just to remind you again what the coefficient of kinetic friction is. Okay, so there it is. That's our little bit on friction. It's really not the full story, both because I can't show you the vector calculus that really nails the work due to friction, and also I have to complete the story because I got to tell you about work. But we will do that, as I said, next semester when we study thermodynamics. Okay. All right. Thank you very much for listening.